¿Quién Barrón?
Esa no es de...
No, si es Barrón, pues él es el organizador, debería de...
Debería de estar ahí.
¿Quién? Caballero.
Ah, el caballero de caballero. Sí, ya ves que siempre hablaba.
Sí, a nosotros cuando tomé clases hace muchos años, nos hizo ir a las pirámides.
¿Verdad? Ah, sí. Oh, qué caro. ¿Y no hicieron ceremonia?
Pues casi.
Sí. Y las preguntas aquí, se me salió, pero ¿qué voy a hacer?
Yo voy a hacer
Para hacerle las preguntas. Pues sí, preguntan.
Pues sí, no, yo no pregunto.
No sé si ¿qué? ¿Falló la cámara?
Sí.
Hay que preparar otra. Sí.
No, aquí hay otra.
Hay otra. No, pues es que lo dicen que falló. Hay que marcarla.
¿La que falla?
No, sí, la que falló, la que no falló.
Hay que romper. No sé, no sé.
Suéter y ahí. Seguro, ¿verdad?
Hi, Shweta. How are you doing?
Hello. Hi,
Can
I'm
you hear
good.
me?
Yes, I can hear you. How are you?
I'm doing well, thank you. Thanks a lot for being here with us.
Thanks for inviting me.
No, you're always welcome. We're still waiting for some people, so let's take
Okay.
some minutes.
Sure.
Mi hermano al menos debe...
Ya. Sí, porque se espera la gente. Sí, porque no tengo ningún estrés. ¿Ya? ¿No sirve?
No,
¿Les falta?
pues estoy esperando a mi hermano,
Al menos que él esté.
Sí.
Ya si no hay nadie, no importa, pero.
Sí, no, pues ya nosotros, pero... ¿Te graban las pláticas? No, ¿verdad?
Claudia y Shell las graba, ¿no? Las pláticas, sí, las sesiones, ¿no?
Es que en la solicitud viene, ¿no? Cuando hacen la solicitud,
Ah, sí, ya
les
sabes.
piden que graben.
Exacto. Si no hacen la solicitud, no graban, ¿eh?
No.
Pero al menos la transmiten por WhatsApp.
Ah,
Yo la subo por YouTube, ¿no?
y pues ahí sí se queda.
Porque me dijo tu esposa que te iba a ver.
Y se transmite por YouTube y ahí quedan
¿Sí?
evidenciando.
Ah, pues ahí está. ¿Qué son cliques? Content cliques.
Son grafos completamente conectados.
Grafos. En el mundo real.
Los grafos normalmente pueden representar el mundo real.
Ujú.
Nada más una estructura de que todos están conectados con todos.
Ya.
Incluso por ahí una foto de entonces estaba sí, gracias a eso, también como que ya tenía como que los avances. La razón de ese
Ahí están más adelantados.
y ya se habló
Redes neuronales o ya no ven nada de eso. Simplemente manejan ya otras cosas, otros términos que aquí no se conocen.
pues, por ejemplo, esto es mucho más teoría que casi no hacemos. Sí nos gustaría hacer más, más teoría y no tanta aplicación.
Aplicación. Pero por ejemplo, para ahorita que se está utilizando mucho la inteligencia artificial, la robótica y todo eso, es interesante, ¿no? Porque ya ven los chinos como que ya están adelantándose bastante, ¿no? Ya mandaron hasta su satélite y
Sí, sí.
su araña ya a la luna, ¿no? Es más interesante. Hola.
Pues, si no,
One question, Ricardo. What time are we planning to start?
just give us a couple of minutes. We're waiting for some more people.
Okay.
Bueno, pero quién sabe. Se me interesa.
Pues sí, debería.
¿Por qué dices que es más interesante ahorita la teoría?
Lo que pasa es que el otro como que tú puedes hacer experimentos y pueden funcionar o no, porque como que vas navegando a ciegas. Y si hay una teoría que te va diciendo, o sea, que ya puedes demostrar matemáticamente que sí va por aquí o que no va por aquí, pues ya más fundamento para entonces,
Ya.
si no es como
Pero-
que echar un montón de largos sobre cuáles.
Claro. Pero si tú, por ejemplo, ya tienes esos fundamentos, ya tienes esa teoría bien cimentada, que no
Es
ya
que
la
para
podrías
que
echar a
sepas, luego, por ejemplo, para muchas cosas no hay esa teoría. Entonces tiene que desarrollar, pero
Sí, porque antes en la escuela era al revés. O sea, te daban un montón de teoría. Bueno, ahora, ya que conocen esa teoría, ya aplican. Laboratorio. Pero sí, pues es que hay un mundo, ¿no? De información. ¿Quién sabe cómo está la educación en Estados Unidos? Ya se van por otros lados. Creo que no es lo mismo. O es similar.
Pues en unas partes, ¿no? Pues
¿Verdad?
intentamos echar ganas.
Sí, ¿verdad?
Echar ganas para que no pase eso. Pero precisamente esto es como una colaboración
Para ver lo que hay ahí.
tratar de empujar
Claro.
un poco eso. Pues creo que
¿Se puede hacer eso? ¿Tú también? Para que vayan a pensar, eso cómo se relaciona con la vida de
I think just a couple of minutes and we start. Sorry for.
Sure, no worries.
No me di cuenta, no sé por qué te hiciste. Ahora.
Ok, entonces yo creo que ya vamos a empezar. Entonces voy a presentar a la doctora. Are you ready, Svetas? Can I present you?
Yes.
Okay, so it's my great pleasure to introduce Dr. Shweta Jain. Shweta earned her PhD from the University of California, Santa Cruz, where her dissertation was recognized as a runner-up dissertation for the prestigious Best Dissertation Award by CKDD. Following her doctoral studies, she pursued a postdoctoral fellowship at the University of Illinois, Urbana-Champaign. She then served as a visiting scientist at the renowned Simmons Institute for the Theory of Computing at UC Berkeley. Today, Shweta is a Computer Innovation Fellow at the University of Utah, where she continues to make significant strides in combinatorial optimization, graph mining, and algorithms for massive data. Please join me in welcoming Dr. Shweta Jain. Go ahead, Shweta, and thank you for being here.
Thank you very much, Professor Menchaca and Bernardo, for inviting me. And thank you all for being here. I'm very happy to be here. So I'll be sharing a glimpse of some of the work that I've done over the past several years. I am working through a sore throat, so I apologize if I pause in between. Okay, so to set some context for this work, we know that graphs are everywhere, right? We have social networks, protein interaction networks, citation networks, routing networks, epidemic spread networks. Now, these graphs, they are sources of rich sources of information. And so, obviously we want to try and glean some insights from them. To be able to do that, we often say we want to solve something like community detection. We want to find what are the communities in this given, say, social network graph. Oftentimes, to solve this problem, under the hood, we have to solve another graph theoretic problem, in this case, something like 10 subgraph discovery. And this is the case for many applications. If you talk about search, under the hood, you may have to solve graph isomorphism. For something like deadlock resolution, you may have to solve directed feedback vertex set or edge set. And for something like routing, you might have to solve shortest path. Many of these, so at the core of many of these applications are graph theoretic problems. And many of these problems are actually NP hard. So it's a natural question that we encounter these NP hard problems in everyday life on real world instances. And so how do we solve them? Is there any hope for being able to solve them? What complicates matters even further is that the sizes of these graphs are often very large. This is partly due to the fact that we are given in the last 2 decades or so, our capacity to store information has increased and gather information has increased. So the graphs that we deal with today are often in millions, if not billions, of vertices and edges. And so for such graphs, even an algorithm that runs in, say, time of n square becomes infeasible. So is there any hope for being able to solve these NP-hard problems with at least some accuracy on these massive real-world instances? So fortunately, these real-world instances, they show some common properties like small world property, meaning that you may have heard about this saying that on average, any 2 persons on Earth are 6 hops apart if you consider the graph of who knows who. These real world graphs, they have some other properties as well. For example, they have a very large number of triangles in them. So for example, if you take a random graph or you take a social network of a certain size and you take a random graph with the same number of vertices and edges, the number of triangles that you will observe in the real world graph will be much higher than the number of triangles you see in the random graph that we picked. Another property that they show is that their power law degree distribution, their degree distribution looks like a power law. So in the middle figure here in the bottom row, this is what the degree distribution of a random graph would typically look like. But for real world graphs, it looks as the picture on the right. So for example, consider Twitter and consider, how many people follow a certain person. Most people will have, on an average, like 100 or 500 or so followers. But then we have somebody like Obama or, I don't know, Justin Bieber, who has like millions of followers. So the degree distribution actually looks like this parallel distribution. So where this work lies is we want to try and use these structural properties, these common structural properties that we observe across real world graphs to be able to design practical and provable algorithms. Okay, so the goal is we want to design algorithms. We want them to be efficient, and at the end of the day, we care about how they actually work on real world instances. And hopefully, we can also give some guarantees about their behavior. So just to give a very brief glimpse of what we can do or what is possible in this realm, we're going to talk about this problem of counting cliques in real world graphs. And these are 4 real-world graphs that I've considered here. ComOrkut is a social network. The others are web page graph. ASKitter is autonomous systems. And the state-of-the-art method. So here we are basically we want to count how many cliques there are of a given size, and we'll go into the depth of this. So if you don't know what clique is, or that's totally fine. We'll look at it in a bit. But basically, the state-of-the-art method, even with, for example, for Bergstein, even in more than 100,000 seconds, it was not able to find the count of all cliques. And this method that we'll look at today was able to do that in 25 seconds. And this is all on a single commodity machine. So we're not using any cluster or anything. Okay, so now I will dive into what these are. So a k-clique is basically a set of k vertices all connected to each other. So a 3-clique is also called a triangle, and we can have 4 cliques, 5 cliques, and so on. And the reason cliques are important is because they often have some semantic meaning in the context of the phenomena that the graph represents. So for example, in the case of a social network, a clique of size 5 could point to a set of 5 friends, and so on. And okay, so these counts of patterns, they can actually tell us something about the process that generated these graphs, where these graphs could potentially have come from, what do they look like, how are these vertices organized in this, in whatever phenomena this represents. They've been used in many different applications, in social network analysis, in social sciences, in topology, in bioinformatics. They've been used for things like graph visualization, dense subgraph discovery, graph classification, and so on. So it's been used in many applications. Now, when we talk of click counts, we can talk about them in multiple different ways. So we can talk about global click counts, k-click counts. So that's the count of k-clicks in the entire graph. Or we can talk about local k-click count. So that's the number of cliques that every vertex or every edge is involved in. And these are called local cliques. And one can imagine that they could be useful in application where, say, we want to weigh the vertices and edges proportional to the number of cliques that they are a part of. So here I have a small toy example, and I've listed down all the local cliques of 1. So all the cliques that 1 is a part of. Okay, so our problem definition is pretty simple. It's simply that we're given a graph G, and we want to be able to count all k cliques in G. We'll set some terminology. We'll use n for the number of vertices, m for the number of edges. Alpha is the degeneracy of a graph. So it's a parameter that appears in a lot of the running time of a lot of algorithms. The important thing to remember is that typically for real world graphs, the degeneracy is small. So these graphs are sparse, and degeneracy is a measure of the sparsity of the graph. And so even for like graphs that are 1 million vertices, degeneracy is typically in the hundreds or the thousands, or even lower at times. Formally, if you define it as it's the maximum min degree over all subgraphs of G. But we don't need to go into the formal definition. All we need to know is that it's a measure of how dense the graph is, and for real world graphs, it is small. Now, a lot of work had been done for counting triangles or 3 cliques, but not much of that could be generalized to cliques beyond size 3. They were able to push it up to 5, but not much beyond 5. And the reason for that is combinatorial explosion. Essentially, as k increases, the number of k cliques tends to increase exponentially. And so these numbers become too large to enumerate, and we can try and approximate, but then there are other problems that occur because of it. Approximation often tends to fail as k increases. Okay, to let you know what some of the background for click counting. So there's a trivial algorithm that given k gives you all the k clicks of size k in time n to the k plus 2. There's also a trivial algorithm that in exponential time will do this for all k. The first improvement was given by Chiba Nishizaki. And basically given a k, so this is a click enumeration algorithm, and its runtime is in terms of alpha, where alpha is the degeneracy that we saw earlier. And we'll actually look at this algorithm briefly today. Our follow-up work, Pivoter, was able to improve the runtime of, so for Pivoter, basically gives the count for all k. And for all k, the runtime improved to n times 3 to the n over 3. We'll look at this algorithm also today. It's a fairly simple algorithm, but surprisingly powerful in practice. Okay, so as I mentioned, there was some existing work that tried to extend it beyond k equals 3. Most of these were approximation algorithms, and the problem with them was they typically worked up to k equals 5. Beyond k equals 5, there was a distributed algorithm that was able to count up to k equals 8. We introduced Turan shadow, which was a sequential algorithm. So it was not run on a cluster or anything, but it was an approximation algorithm, and we were able to count up to k equals 10. Then there was KC list, which was again a parallel algorithm, and then there was Pivoter, which was able to give the count for all k clicks, and it was able to give the count, the local counts as well as the local counts. There were also some works that came out around that time. So we'll basically look at both Turan shadow and Pivoter and the click enumeration algorithm of Chiba Nishizaki today. Okay, so diving into Turan shadow, the problem for this is essentially the same. We're given a graph J and a positive integer k, and we want to obtain all global k click counts. So what we presented was a randomized algorithm called Turan shadow that approximates the number of k clicks, and it has the following nice properties. One, it runs on a single machine. So all our experiments were conducted on a single machine, single commodity machine. We didn't have to use a cluster or any such thing. It works well for up to k equals 10, and it is also able to give we are able to sample a random k click. So for some applications, this can actually be useful. So that's just an additional thing it provides. So before we actually look at the algorithm, let's look at this interesting question that Turan asked in 1941. He asked, how many edges can an n-vertex graph have without having a triangle? So here we have a bipartite graph. It has n squared over 4 edges, and it does not have a triangle. And Turan and Mantel showed that if the graph has more than n squared over 4 edges, then it must have a triangle. And then Edo showed that if you have even one more edge than this, then in fact, there are many triangles, at least of the order of n triangles. So as soon as you put this one edge, suddenly you create a lot of triangles. If we talk in terms of edge density, so where by edge density we mean the number of edges divided by n choose 2. So if the graph is empty, basically your edge density is 0. And if the graph is a click, your edge density is 1. So one can imagine that starting from an empty graph, as we go on putting edges, there comes a density point beyond which we just cannot avoid having a triangle in the graph. And that is this point. So beyond n squared over 4 edges, we just cannot avoid having a triangle. And this density is also called the Turan density. So Turan density for n and 3, meaning where given a graph on n vertices, the density at which you just cannot avoid having a three click. And this comes out to roughly half. And so essentially what their theorem is saying is that if the density is greater than the two-run density, then the graph necessarily has at least of the order of n triangles. And they generalize this for larger k. So meaning that if the two-run density is greater than this quantity, which roughly comes out to 1 minus 1 over k minus 1, then it must have at least of the order of n to the k minus 2 k cliques. So that's a lot of k cliques. Okay. So how does that help? And can we maybe use this fact? We'll look at this later. The important thing to note here is that if a graph is two-run dense, meaning that it has density greater than this density bound that the theorem gives, then we are guaranteed that there are many k cliques in the graph. Okay. So coming back to our problem. Okay, so we're given a graph. Let's say we are given a graph of 1 million vertices, and we want to find the 5 cliques in this. So a simple thing that we can try is to just sample 5 vertices randomly, check if they form a clique. If not, we sample another set of 5 vertices. We continue this process until we find a clique. So let's say the number of 5 cliques in this graph is of the order of, say, 100 billion. Which is roughly of the order that we saw earlier in the table. The expected number of samples that one would have to take to be able to see a clique is 1 million choose 5 divided by the number of 5 cliques, which comes out to roughly 10 to the 16. So this is simply to use a number for us to be able to find a clique using this sampling process, and for us to be able to do this on a commodity machine. So what is really happening here is that real-world graphs are very sparse. The number of edges that are there in these graphs are pretty small. And so what happens is any 5 vertices we pick, the chances that all 5 of them are going to be connected is very, very small. And which is why the number of samples we have to take before we actually see a clique is very large. Okay, so sparsity hurts us here. But real-world graphs do have this property that the edges of the graph, they're not strewn randomly all over the graph. They're not random graphs. These edges, they tend to be concentrated in dense pockets. And so if we can somehow drill down on these dense regions and look for cliques within them, then we'll be able to find our cliques faster. And that is essentially what our first algorithm, two-run shadow, does. So given a graph G, we decompose it into smaller subgraphs, G1, G2, G3, and so on. These subgraphs can be overlapping. With each GI, we specify a KI. Think of KI as an integer between 1 and k, where k is the size of the clique that we are interested in counting. And this two-run shadow, it has 2 nice properties. So I'm not going to describe how we get this shadow, but I am going to describe the properties of the shadow and how we use it. So the density of each GI is guaranteed to be greater than the two-run density for the corresponding KI. Okay, so all of these subgraphs are dense. And the other nice property that they have is that there's a bijection between the cliques in the given graph, the k cliques in the given graph, and the ki cliques in each of GIs. And so one can write that the number of k cliques in G is actually equal to the sum of the number of ki cliques in each of these GIs. Okay. So because of these 2 nice properties now, so because of bijection, the revised goal now is to essentially estimate the number of ki cliques in each of these GI. And the first property now, because our GIs are dense, we can use sampling. And because we have a bound on, we can say that, okay, this subgraph on ni vertices is guaranteed to have at least these many ki cliques. Now, when I sample, I know that the number of samples that I'll have to take the number of that is bounded and is not too large. That's essentially how it proceeds. So we create the shadow, and then for each of these, so actually we do some more things on top of it. One can actually show that we don't need to find the ki cliques in each of these GIs. It suffices to sample from them and then find the ki cliques in those sampled subgraphs. And we essentially get pretty good results in practice because of it. So one thing that came out of this work. So this is a plot that shows the number of edges on the x-axis, the shadow size, meaning so for each subgraph, look at the number of vertices in that subgraph, and you're counting that over all the subgraphs in the shadow. So that quantity is on the y-axis, and this diagonal line represents x equals y. And here we've used the shadow sizes for k equal to 7. And each blue dot here represents a real world graph that we tried this for. So in the worst case, our shadow size could have been of the order of n to the 7. But what we observe is that the shadow sizes are roughly proportional to the number of edges. And for real world graphs, typically the number of edges is linear in the number of vertices. So essentially, we are saying roughly order of n vertices in our shadow, which is a surprisingly small shadow. So what that says is that there is some structure, some nice structure here that we don't quite yet understand. And it's an interesting question to try and find out what's really going on. Like, what is the structure that is leading to such a small shadow for this? And this is something we observed in our later algorithm also. In terms of the practical runtime, so here I've shown speed up, which is I have the different graphs on the x-axis, the time taken by the other algorithm divided by the time taken by to run shadow on the y-axis. And for a lot of these graphs, we were able to see a speed up of up to 100x, and in some cases even more. Okay, so we actually generalize this to counting near cliques also, where by near cliques in this case, I mean cliques that are missing 1 or 2 edges. Essentially, the observation was that every near clique has a clique sitting inside it. So if we build a shadow for that clique, then and we say sample a clique of that size, we then look at its neighboring vertices and get a sense of how many near cliques that clique is involved in. And we do this several times and then take the average. So, okay, so that was to run shadow. This next work that I'm going to talk about is also about clique counting. The problem here is, again, we're given a graph G and we want to obtain global and local k clique counts in this case, for all k. So here we don't assume that k is given to us as an input. We want to do this basically for all k. And what we were able to give was an exact clique counting algorithm called Pivoter. In practice, it was more than 1000x. It gave us more than 1000x speed up even over other parallel algorithms. It gives global and local counts. It works for all k for a large number of graphs that we tried in practice. There are graphs for which it still does not. It is still not able to get us all the k clique counts within a reasonable time. But for most real-world graphs that we tried for, we were able to get. And it reduced the theoretical worst-case running time of clique counting from n squared times 2 to the n to n times 3 to the n over 3. So we'll look at what this is, but before we do that, it would be useful to get some intuition for how cliques behave. So cliques are recursive structures, meaning that the subset of a clique is also a clique. So what that suggests is that we can find a small clique So let's say I found this clique that has red vertices. I found this small clique, and then we can look at the set of common neighbors of this clique. And then from the set of common neighbors, we can pick a vertex to add to our clique. So now the clique has become of size 4. And now we look at the common neighborhood of this clique of size 4, and so on. So we go on building these bigger and bigger cliques, starting from small cliques. And if we do this process exhaustively, then we will have discovered every clique in the graph. Of course, we will have discovered every clique multiple times, but there are ways to deal with that. But so all of these algorithms, the other algorithms that I mentioned, KC list, count cliques, pivoter, and also Chiba-Nishizaki, these are all recursive backtracking algorithms that visit every clique. So we'll first look at this algorithm of Chiba-Nishizaki because, as I mentioned, pivoter is essentially built on top of this. So how does this algorithm work? Given a graph, we number the vertices of the graph, and we convert it into a DAG by orienting all the edges from lower vertices to higher vertices. Okay, so I've shown the DAG here. And now there is one can show that counting the k cliques in G is actually equivalent to counting the number of k minus 1 cliques in the out neighborhood of each vertex. So we have this DAG on the right. And now for every vertex of the graph, we will look at the out neighborhood of that vertex. And now we are interested in counting the number of k minus 1 cliques in these out neighborhoods. Okay, that's essentially what this theorem implies. And so notice that essentially we are interested in solving the same problem, but on smaller instances and for smaller k. So what do? We recurse. So for every vertex in these out neighborhoods, we spawn a branch, calculate the new out neighborhoods. So now 6 and 8 are actually in the common out neighborhood of both 1 and 5. Sorry, was there a question? Okay. So 6 and 8 are in the common out neighborhood of both 1 and 5, and so on. And so this process, it continues. So we again, now in this new out neighborhood that consists of 6 and 8, we are now interested in counting the number of k minus 2 cliques. So remember, we started with wanting to count k cliques. At the next level, we are interested in counting k minus 1. Level beyond that, we are interested in counting k minus 2, and so on. Okay. So essentially, the thing to note is that at every recursive call, we have a subgraph at hand, and we are interested in counting the cliques in that subgraph. And this process continues until there are no more subgraphs left. And at the end of this process, what we get is what we call the recursive enumeration forest. Okay, so for the given graph, the recursive enumeration forest would look something like this. Now, this recursive enumeration forest, it has certain properties. All the nodes of this forest, so I'll use vertices for the vertices of the graph and nodes for nodes in the tree or the forest. All the nodes at level 1 represent cliques of size 1. All the nodes at level 2, they represent cliques of size 2, and so on. And in fact, any path you take from the root to any node at a given level represents a clique, a unique clique in that original graph. So for example, here I marked the largest clique 1, 5, 6, and 8, and there is exactly one path that has those vertices on that path. Okay, so that clique is represented by this path. So all k cliques are at level k. Every green vertex here is a recursive call. Every green node, I should say, is a recursive call that the algorithm makes. And so what this says is that the total number of recursive calls that this algorithm makes is equal to the number of cliques in the given graph. There are some things you can do, some optimizations to reduce this number a little bit, but essentially this is saying that the number is very high, and we've had graphs that have had like 10 to the order 10 to the 40 uh, cliques, so cliques of this order. And so, enumerating these is simply not a feasible option. And so what other methods try to do is they truncate at a given k, and so they count only up to that k, or some of them use parallelism, but there's only so much that can buy. So we were interested in asking this question: can we count without enumerating? Okay, so is there any hope for us to be able to do that? So we use this idea of pivoting. Okay, and the problem with enumeration was that there are simply too many recursive calls. We use pivoting to compress this forest. And here by compression, I don't mean in the sense of file compression, but actually making the nodes in the forest decrease. So we want to make far fewer recursive calls. And while we are doing that, we want to do it in a way that we are able to keep track of exactly how much we have compressed. So we still want to be able to count all cliques, just that we want a smaller representation of the first. Okay, so we use this idea called pivoting. This idea of pivoting was not new. It was actually already used for finding maximal cliques. And in fact, it saw great success in being able to find maximal cliques. So as I mentioned earlier, in clique enumeration, we explored the out neighborhood of every vertex, right? What pivoting is that there is a way of ordering the vertices such that some of the trees can be folded into the out neighborhood of a pivot vertex, and those trees that were folded in, they need not be explored. I know this is a mouthful, and don't worry if this doesn't make sense. We'll actually look at an example and work through it. Okay, so how does this work? So given a graph, we pick a pivot. So in this case, I've picked the vertex 1, and we order the vertices according to this ordering. So the non-neighbors of 1 followed by 1 followed by the neighbors of 1. So that looks something like this for this given graph, and 1 as the pivot, all the non-neighbors of 1 followed by 1 followed by the neighbors of 1. And what the enumeration algorithm would have done is it would have looked at the out neighborhoods of all of these vertices, and this is what the out neighborhoods would have looked like. But we noticed that 5 and the neighbors of 5 are actually present in the out neighborhood of 1. 6 and the neighbors of 6 are present in the out neighborhood of 1. 8 and the neighbors of 8 are present in the out neighborhood of 1. So essentially what this means is that when we are exploring the out neighborhood of 1, we are already discovering the cliques that the enumeration algorithm would have discovered in the trees of 5, 6, and 8. So any clique that the enumeration algorithm would have found in the trees of 5, 6, or 8, it is already being discovered here in the out neighborhood of 1, in the subtree of 1. And so we need not explore the cliques of 5, 6, and 8. What we do need to do is, for every clique that we find in the out neighborhood of 1, we need to keep track of, we need to basically count it twice. And we need to say that, okay, this represents once a clique including 1 and once a clique that does not include 1. So the clique that does not include 1 is the clique that the enumeration algorithm would have discovered in the trees of 5, 6, and 8. And so this pivot vertex, the vertices, they are special kinds of vertices. We can think of them as yes/no switches to the question, do we want to include this vertex in the clique? So if we include 1 in a clique that we find in the neighborhood of 1, If we include one with that, then we get a different clique. And if we don't include one, we get a separate clique. But the uniqueness and the one-to-one mapping is still maintained. So yes gives a clique from this tree, and if we choose to not include one, then that gives us a clique that the enumeration algorithm would have discovered in the trees of 5, 6, and 8. And now notice that at every recursive call, we basically have the same situation, right? We have a subgraph. We're interested in counting the cliques in that subgraph. So we can apply pivoting at every recursive call. And the resultant tree that we get, the resultant structure, is what we call as the succinct clique tree, or the SCT. So where the enumeration forest looks as what's on the top, the SCT looks as what's below. And one can see that there are far fewer recursive calls, and this is where the savings in runtime come from. And here we took a small toy example with not very big cliques, but one can imagine that in a bigger graph with bigger cliques, we can actually get substantial savings. Okay, this SCT, it has what we call as the unique clique encoding property, meaning that every unique configuration of yes, no on a given path. So with the green vertices, we don't have a choice. They're not switch vertices, but the red vertices are switches. And so every combination of yes and no gives us a unique clique in the original graph. And for every unique clique in the original graph, there is exactly one path and exactly one configuration on that path that gives us that clique. Okay, so there's this one-to-one, this bijection we still maintain. And as I had mentioned earlier, even for, so we looked at the size of the SCT, the number of nodes in that structure, the tree structure that it builds. And that I've represented here on the y-axis on a log scale. On the x-axis, we again have the number of edges. The diagonal line represents x equals y. And again, we saw that the blue dots represent different real-world graphs that we tried this for. And the size of the SCT was roughly proportional to the number of edges. So this corroborates what we found earlier and still points to this question of what is this structure. In terms of practical runtime, so here I have 4 large real-world graphs, and basically the only method that was able to count up to beyond 10 was this method KC list. Basically, it was a parallel algorithm, and you give it a k, and it gives you tries to give you the count for that k. So we took the max k for these 4 graphs, which were 61, 201, 67, and 51, and we fed that k to KC list, and we saw how much time it required. Whereas, so the light blue lines, the blue lines represent the time taken by pivoter. The lightest blue lines represent the time taken to count all cliques, and the darker ones represent the time taken to get the per vertex and per edge count. So it takes some more time, also because there's a lot to be output. But essentially, what we observed was that for 3 out of 4 graphs, we were able to get all k-clique counts in minutes. For one graph, it took about a couple of hours, whereas the other method had not terminated even after 3 days. So basically, this compression is able to work very well for these real-world graphs. So as I mentioned earlier, this raises an important question, as in why is click counting and near click counting so fast in practice, much faster than what we expected initially? So there was some subsequent work which tried to give a theoretical explanation for what may be going on. So as I said, clearly there is some structure here. A graph class was introduced called C-closed graph. And this graph class was inspired by real-world graphs. Essentially, it tries to capture this phenomena that we observe which is called triadic closure, which is that a friend of a friend is likely to be a friend. So in other words, in real world graphs, a lot of these two paths tend to be cliques, tend to be triangles. So what this formally, what this graph class says is that we say that a graph has C closure if every pair of vertices that has C or more common neighbors, they're themselves connected. So meaning that there is no, we say that a graph has C closure C, some particular value C, if any two vertices that are not connected, they have at most C minus 1 neighbors. If they have more than C, C or more than C neighbors, then those two vertices have to be connected. Okay, so that's basically what it says. So if we have these vertices UV and it has more than C neighbors, then we can assume that U and V are connected. Now, what we essentially show is that enumerating the maximal cliques, and that has connections to essentially this algorithm that we showed, but we showed that this algorithm is FVT with respect to C. What does FVT mean? So some NP-hard problems are such that we are able to find algorithms for them whose running time can be given in terms of K, where K is some parameter, and such that the exponential part is with respect to K and not with respect to N. So typically, so instead of having something like, say, 2 to the N runtime, you would have something like f of n times 2 to the K. F of n is typically a polynomial function in N. And here, instead of 2 to the N, you would have 2 to the K. And K is, if K is much smaller than N, then one can hope that these algorithms will work fast in practice. And so here for us, K was C, and what we showed was that the runtime of this algorithm that we looked at is actually of this form. And if you look at, right, so the C values for real world graphs are typically pretty small in tens. And so essentially, instead of having 2 to the N in the runtime, we have 2 to the C in the runtime. And that, to some degree, explains why our algorithms are fast. Because essentially, this problem is FVT, and this algorithm is, it has an FVT runtime. So in this way, it helped bridge the gap a little bit between theory and practice, between what we were observing in practice and what we thought might happen, theoretically speaking. So I will summarize my talk here. We talked about Turon Shadow and Pivoter, which leveraged the properties of real-world graphs, and they were able to improve the running time of click counting, both in theory and practice. And we also looked at the C-closed model, which to some extent was able to explain why we are able to do click counting efficiently in these graphs. And I will end my talk here. Thank you.
I don't know if you have any questions. And I don't know if they have access to the chat for the people that are remote. I'm not sure.
We have access to the chat, Ricardo.
Okay, thank you. So, are there any questions in the chat?
No.
I have a question.
Mhm.
I have a couple of questions, Isweta. First of all, thanks for having this meeting with us. Thanks for being here with us. Both algorithms are really interesting, with very interesting ideas underlying them. Thanks for explaining them to us. So I have two questions. The first one is, and actually it's not related specifically the algorithms, but to the ideas that you have exposed. The first one is about how to think about the number of K clicks versus the size of K. Because in some sense, I think that I read in some part of your paper, or I don't know if also in the slides that you share with us, that it's believed that the larger the number of K, the larger the number of K clicks. But in some sense, intuitively, for me, it's actually the opposite, because in order to have a click of size, let's say 10, I think, or at least in my mind, you need to meet more conditions that in order to have a click of size 9, for example. Do you follow my question, Shweta?
Yes.
So that would be my question, is like how to think about this?
Yes.
What is the intuition behind this?
Yeah. So let me answer this first, and then maybe we can get to your next question.
Yes, for sure.
Okay. So two things. One is when I said that the number of clicks goes up as K increases, I cheated a little bit in the sense that it actually looks somewhat like a binomial distribution. So starting from a small value of K, as you go to say, a moderate value, it goes up, but it goes up pretty fast, like exponentially. And then at some value of K, it basically at the max click size, whatever that is, it typically comes down. So but having said that, it is natural to think that, to get a 10 click, you need 10 vertices. And within a 10 click, there are many 7 clicks sitting, for example, right? So how can it be that the number of 10 clicks is greater than the number of 7 clicks? So for that, I will give you an example. Think of let's say your graph is a graph on 100 vertices, okay? And suppose it's a click. The whole graph is a click.
Okay.
Now, how many 7 clicks does this graph have? It has 100 choose 7.
Exactly.
Right? Which is roughly of the order of 100 to the power of 7.
Agree.
And how many 10 clicks does this have?
N choose 10 in this case.
Correct. And that's roughly n to the
power of 10. Okay, I see it. That's an interesting way of thinking about it. Thank you. Yep.
Yeah. I understand it's very natural way, and it's but yeah, if you spend a little bit of time with it, you will actually see that to create 10 clicks, there are many more combinations that you can take, and which is why the number of 10 clicks ends up being higher.
Perfect. Thank you so much. Actually, that's a pretty good explanation. It's but it's kind of counter. I mean, the fact is counterintuitive in some sense, isn't it?
Yes.
You will expect the opposite to come. At least to me, it's that is my expectation. Okay. Thank you, Shweta. My next question is related to the Turan shadow. Sorry, not to the Turan shadow, to the Turan theorem. And my question is very simple. It's more than a question. It's like something that I wanted to see. What do you think about this? It looks like to me that this Turan theorem, in some sense, is some kind of phase transition theorem. Phase transition in the sense of adding a simple edge. Once you are in the limit, you go from having 0 triangles, in this case, to having at least n of them. So it's like, again, I don't know what other expression to use, like a phase transition. So I would like to just know, what do you think about this? If this is like a right intuition in some sense?
Absolutely. Yes, it's spot on. It is, in fact, a phase transition. Like how you think of connectivity, for example, like when you add edges, beyond a point, you just cannot avoid having connected components, right? So if we observe phase transition even in that, it's a similar kind of phase transition that beyond a point, you just cannot avoid having cliques of certain size. So it is absolutely the right concept. Perfect.
Okay. Thank you so much, Esguera. And again, thanks for being here with us. Personally, I need to drop. I need to go back to work. But again, thank you so much. This is your home. You can come back whenever you want. I don't know if someone else has some other questions. And again, thank you, Ricardo, also for helping us to organize this.
Yeah, thank you very much for organizing this and for inviting me.
Yes,
Thanks
I
to
just
you as
have
well.
a couple of questions. A question at least. Just to understand better your exposition, it was very nice. Like when you talk about these fixed parameter algorithms, like how can you see this C in the formation of this tree that it depends on how hard it is to form the sequence to have smaller trees for counting the clicks, or how is the explosion in the
I see. So basically, this enumeration forest, let me just pull that up. Yeah, okay. So this thing on the top, so actually the bound applies not just for the ICT, but also for the enumeration forest. One thing we can say right away is that if a graph is C-closed, then the depth to which it can go before your subgraphs themselves become cliques. So if the subgraph that we're looking at, that itself is a clique, then we don't need to explore it further to be able to count the number of k cliques in it. We can just take whatever the size of that subgraph is, that choose k, and that's the number of k cliques there, or ki cliques there, whatever ki we are interested in. So in some sense, we can think of it as a terminal case. Like if the subgraph we're looking at, if that is a clique, then we just stop and we move on to the next branch. So the first thing that we can say is that the depth of this tree or the enumeration forest will be at most C, and that's something we can show. But there's more we can show actually. It would take a little bit of time. So basically, what it says is any missing edge. So okay, the subgraphs. Let's say when the subgraph becomes a clique, we call those leaf nodes. Okay, so beyond that, we don't need to explore that subtree any further. So now we need to look at how many non-leaf nodes there are. Non-leaf nodes have to have at least some missing edge in them. Now, because they have a missing edge, the vertices on the path, those vertices have to all be common neighbors of that missing edge. And because we are in the C-closed setup, we know that we are allowed to have at most C common neighbors, right? And so given a missing edge, we can have at most 2 to the C subsets that we can pick from the neighbors of that missing edge. And so essentially the runtime or the number of nodes in this tree becomes the number of missing edges times 2 to the C. For every missing edge, we can have at most 2 to the C. And so the total number just becomes the number of missing edges, which can be of the order of n squared times 2 to the C. I don't know if that makes sense, but
yeah, a little bit. I think
yeah, okay.
But then thanks a lot.
Yeah, there is another talk actually that's available on YouTube. It's on the C-closed algorithm and the C-closed work. That might give you some more information.
And perhaps a little bit of more general questions, like more, like for example, is there a relation between these trees and maybe a graph decomposition of the graph?
Graph decomposition of the graph, yes. So the Turan shadow is essentially a decomposition, but it is not a partition of the.
Sorry, I mean like a tree decomposition, like when you use also for parameterized algorithms, like the tree width as a parameter.
Oh, I see. Okay. That's a good question. I don't know of a connection. Yeah, I don't know of a connection off the top of my head.
Okay, thank you. And the last question, like, what's your opinion on the use of machine learning techniques like reinforcement learning or graph neural networks to solve combinatorial optimization problems? Do you think that there is some hope that we can use those techniques, or?
I mean, there is some upcoming work that tries to do that, but fundamentally there is this, I mean, if we want guarantees, then, through those methods, we won't be able to get guarantees. But of course, those methods have other advantages in the sense that the runtimes can be pretty fast if we get it right. But if you are looking for at least some kind of guarantee, even when approximating, as in how far could I possibly be from the real number, then I think we'll have to rely on these kind of more algorithmic approaches, more combinatorial approaches.
Okay, thanks a lot.
Sure.
I don't know if there is any more questions. Well, thanks a lot again for your talk. It was very nice.
Thank
And you're
you.
welcome here, maybe in person at some point. And you want to visit Mexico.
Yeah, I'd love to at some point. Yes, hopefully.
Okay.
Yeah.
Good.
Hello?
I don't know what was it.
Sorry, I think the audio dropped for a bit for me.
Are we gonna send you a diploma for the talk?
Okay, great.
And thanks again.
Thank you. Thanks. Okay, bye.
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 Ya, vamos a seguir invitando, yo creo que. Muchas gracias a todos. Con esto cerramos el ciclo de este semestre de Matemáticas, Computación y Café. Bueno, en enero les vamos a hacer llegar a todos el calendario, digamos, de las charlas para el próximo semestre. Esencialmente, los que participamos este semestre vamos a descansar. Nada más tu canal, sí. El problema es tardísimo. Igual la NP va a ser un trabajo. Es un reto a ver que lo aceptó, a ver si por lo demás, la idea es que varios profesores que no pusieron les pongan, incluyendo algunos que no quieran. Por supuesto, ya lo vamos a considerar que es una excelente charla. La última pregunta que estuvo muy buena.
Nos interesa.
Entonces, bueno, seguimos en eso. Muchas gracias por todo y un aplauso por todos. Cerramos. Sí, ya.
A ver si dice.